Well, I didn't realize I'd run out of time. So I have a little bit left of this slide and one more to go for this section of the lecture. And I think I was talking about the third point on this slide when I got cut off. So the mass of an individual atom is close to a whole number of mass units. However, the atomic mass is determined from an average sample. The atomic mass, which is determined from an average sample of atoms, does not have to be. It's the weighted average of those naturally occurring isotopes. It's, I think, almost always a decimal measurement. So the mass of isotope carbon-12, so that's carbon with 6 protons and 6 neutrons, the most sort of abundant version of carbon on Earth, is now used to define the mass unit. And one mass unit is defined to be 1/12 of the mass of the carbon-12 isotope. So the strong nuclear force is holding those atomic nuclei together. The strong nuclear force is also holding the gluons that make the nucleons together, but we'll talk about that in a minute. So protons and protons are positively charged, and the electrostatic force is repulsive for same charged items. So a proton and a proton getting real close together in a nucleus experience a huge repulsive force, like charges repel. But fortunately, nucleuses don't tend to fly apart, at least under most conditions, because an even stronger attractive force exists within the nucleus. So there's a force that's fighting that electrical repulsion once protons get close together in the nucleus. That force is the strong nuclear force. The strong nuclear force is an attractive force between nucleons that get close together, as in the case of a densely packed nucleus. And that strong nuclear force is the strongest known of the 4 fundamental forces. The strong force has a range on the order of 10 to the negative 15th meters. Outside of this range, the effects of the strong force are minimal. So that 10 to the negative 15th meters, the number itself isn't really important, but it gives us the size of a stable atomic nucleus, because beyond that range, we don't really have gluons exchanging. We don't have that strong nuclear force opposing the repulsive electric force. The strong nuclear force has the same strength between all nucleon pairs, but it does not affect electrons. So that just means that neutrons and neutrons are attracted to each other by the strong nuclear force. Protons and protons are attracted to each other by the strong nuclear force. And protons and neutrons are attracted to each other by the strong nuclear force. All of those particles are made up of quarks, 2 up and 1 down, or 2 down and 1 up. And quarks interact with each other via the strong nuclear force. So it sort of makes sense that the things that quarks make up are also, under some circumstances, when they're close together, exchanging quarks as well. The strong force is responsible for holding together the particles that make up protons and neutrons, that being quarks. So this is a big idea. Protons shoved together in a nucleus would tend to not want to be close to each other in a nucleus. They would be repelling each other by the electrostatic force, like charges repel. However, they don't. There's another force at play called the strong nuclear force. Okay, so that's the end of section 1. I'll stop this video, try to combine the two, and next we'll talk about radioactive decay.